primary things, the primary differences, for one is,
hey, sorry, hang on a minute.
Laser and you point it at the window. Every schematic, every laser microphone I've ever seen simply has a constant laser source, hitting something and reflecting back. The problem I found with this is that there's so much noise. We have the 60 hertz noise from the wall. We have all sorts of noise from computers around. And all this stuff is typically low frequency noise that's messing with your signal. And we need to get rid of that. So I found a laser driver. This was a laser driver I had that had something called an RF bias T. And what this means is it's a mixer. So you can have a constant current source that's powering the laser, and then you can have another source that's oscillating. And I was thinking, well, what they do in radio is that they'll oscillate things at different frequencies to get away from other frequencies that might be harming. So what if we turn the laser on and off in the RF domain? If we go into radio, and we're turning that light on and off at the radio frequencies, then we can actually get away from all that noise that we hear. Here you can see the different parts of the system. So the oscilloscope in the top, I use that simply because I have a signal generator built in.
Go up or down?
So Rigol. I'll have the full details, the full bill of materials in a future slide. But the current controller and temperature controller, you do not need a temperature controller, but that's just what I have at home. Current controller for the constant current source. In the top, there's that black box. That's the laser driver. There's also the RF mixer built into that. I use a collimating lens. So what collimation means is, it just takes light and tries to make it into a single dot, or a straight, if you take a flashlight, you typically have an unfocused beam of light. A collimated beam is a beam that does not focus or defocus. I used to think a laser, what made a laser was that it was collimated, that it was a straight line, and that's not true. It's not collimation. What makes a laser is that it's coherent. And all that means is that the phase of light coming out is always the same. It always starts at the same place. It's not important for this attack. I thought that was interesting for me to understand what a laser is. The flexor, that just lets us actually direct the lights up and down very easily. A shutter is to really tighten our beam. So even though we have a collimation, and we're collimating this laser beam, we want to get a really tight beam. So a shutter just lets us close that even further. And behind the lens, there's a laser diode. And all of these you can buy separately. And the nice thing is that with the laser diode, I can use a red light normally when testing, but then I can move to the infrared where we don't see it. So these are the actual components I'm using. The obligatory turn on the fog and check out the cool red laser beam. Then we want to actually receive that information. So how do we receive it? The typical setup is we have a photodiode and a sound card. But what we're doing is we're modulating. So with the signal generator, we start modulating this thing at hundreds of thousands of times per second. So that sound, humans can hear between 20 hertz and 20 kilohertz. So I want that sound. But I want to then get away from those low frequencies because there's so much electromagnetism at those frequencies that it's disrupting the signal I'm getting. Because we're getting very little light back from the laser that's reflecting off a window or off a computer. So first, the sound card can only listen to, say, 48 kilohertz or 192 kilohertz. To get away from all that sound, we modulate the laser. We turn the laser on and off 400,000 times per second. So we're at 400 kilohertz. So we need something other than a sound card that can actually accept this. So first, I thought, okay, well, I can use a bunch of analog components. The problem with analog components and electronic circuitry is it's a huge pain. So as you're putting these little components in the circuit board, for one, you're dealing with high frequencies. So as you're trying to change as you're trying different filters and amplifiers, all of this is very difficult. And think, man, I really wish I could use GNU Radio. GNU Radio is open source signal processing software. And with that, then I can drag and drop, and life is just great. I can sit back in my chair, drink some caffeine, and just play with these blocks, and just test different things to see what works. The problem, the challenge with using GNU Radio is that I need then a software-defined radio to pull that data in. The sound card won't work because I need something that can listen to not only 400 kilohertz, I need to go at least double that. It's called Nyquist's theorem. I need to go to at least 800 kilohertz of a sample rate, how fast I'm listening to that data. And I can use a software-defined radio, but software-defined radios don't ever go that low. So the RTL SDR, I'm not sure where that goes, maybe 100 megahertz, excuse me. The hack RF, amazing, I love the hack RF, but the minimum frequency it can listen to is at about, 1 megahertz, and we're at 400 kilohertz. The USRP, it also has a very low bit rate, so it's about, the analog to digital converter has an 8-bit sample rate. And we want higher samples. We want higher resolution so we can extract more signal. The USRP B210 has 12 bits, which is good, but it requires 70 megahertz, and we're just down at 400 kilohertz. But then I started looking, and there is something called an upconverter that we can get. So the upconverter actually adds 125 megahertz to a signal as long as it's at least 100 kilohertz. So we're at 400 kilohertz. So ultimately what I used was a photodiode. I go into an amplifier. That amplifier then goes into a ham it up, V2. That adds 125 megahertz to our 400 kilohertz. So now we're at 125.4 megahertz. Then I go to the USRP. Now that can go into my computer. Here's the physical setup. This is the receiving side. Lens to capture light, into a photodiode, into the amp, into the USRP B210, into the computer. If you see this outside of your window, it is super sketchy. Maybe like shut the blinds, call the police. But once you actually point this laser at a computer, now there are some big challenges here. Actually performing alignment is very, very, very challenging. Getting sound is actually not so challenging because our ears, we're pretty good at listening to just 1 kilohertz of sound. Although we can hear up to 20 kilohertz, just 1 kilohertz, we can usually make out what someone is saying. Getting above, I'd say, the best I was able to get above was 4 to 5 kilohertz of sound. And I found for keystroke extraction, I needed to get to 3 kilohertz. If I got to 2.5 kilohertz, I could not convert anything to keystrokes. If I got to 3 kilohertz, I could start converting to keystrokes. Here's the hardware on the transmit side, just the actual components, just so you know. Here is the RX side. This will all be online, so if you want to know the exact components I used. And one of the other improvements that I wanted to make here, for one, now that we're getting into the RF domain, we get away from all this noise, and we can actually filter out that noise. Another cool thing is I wanted to do this in infrared. I don't want someone seeing me standing outside pointing a laser into their window. That's just too obvious. So I got an infrared laser diode, and how do I actually align to the infrared? Because I can't see it. So I got this infrared camera. It's the X-Night USB 2S M. It's around $120. It's very cool. It's actually very exciting to be able to see infrared, right? Just being around you. And here's it's maybe hard to tell, but I have the laser diode going and hitting a white square, and you can't see it on my camera, my phone camera, because my phone camera also can't see IR, and my eyes can't see IR. And then here's, just so we can see, I did a recording with that camera, pointing the laser at my laptop, and you can kind of see the reflection. I'm sitting below the laptop with a steam iron, and I'm just like steaming my laptop until, I think it was the first time I ever used a steam iron, until boiling water boiled down on me, and I was like, so I got maybe a few seconds before I burned myself. But while I was doing this testing, I also saw something else interesting. I pulled out my phone, and I wanted to change the song because Spotify was playing. And when I unlocked my phone, I saw these dots, not on the wall, but I saw it on the IR recording. I'm like, wait, what's happening? When I pulled out my phone, I realized this is LiDAR. So my phone is using LiDAR on the back. I'm like, why? Why is it projecting all of these infrared dots that we cannot see with our eyes? And it only happens when the camera app is open. And it's actually very cool. It's figuring out how far is the object? How far is it? And if it's close, it's going to use the close camera. You have a bunch of cameras on the back of your phone. So it's deciding which camera to use. So when you go closer to an object, it will automatically switch to a different camera. And I thought, well, that's really cool. Well, what if I can actually measure this? So I put this in my spectrometer just to see what wavelength of infrared this was. Because now we can just monitor for this wavelength of light. So imagine you have a little device with a photodiode, a photosensor on you, so that whenever someone points their phone camera at you, you get a little vibration. Because you can just measure for that frequency of light and for that on and off path. And now you can know when someone points their phone camera at you before they're even recording. And it only will show, you can see that sort of rectangle, that's exactly the same path. That means I could just make all of you vibrate right now. How fun would that be? So, separate project, we'll do that another time. So there's the RF modulation. This is the biggest improvement that I've seen in this laser microphone. So actually getting into the RF domain. The photodiode I use, this is the Spot 2D. It's pretty interesting. It actually has 2 cells. So where photodiodes are typically 1 pixel, this is really 2 pixels. The biggest challenge of this whole system is that you must get essentially to the edge of the diode. You don't want to get the light in the center, you want to get to the edge. because as soon as the edge, you essentially want your light, your reflection to go on and off that diode. If you're in the center, then you're not gonna get much variation. But if you're at the edge, that's where you get all the variation. There, I noticed there was a hair in their photo. Fortunately, there was no hair in the photodiode they sent me, so I didn't have to send it back.
Well, thank you.
Software that we use. So
Wonder Twin Powers activate.
Awesome software. First, GNU Radio. And we'll quickly go through the steps here, but all this will be online as well. So GNU Radio, all the red stuff on the left, those are just variables. That just makes it easier for me to, just like in software, to use a single variable that will change things in multiple areas.
The AI will unleash, you mean?
Circled in blue, those are just GUI, those are just graphical syncs, so we can see information. The heart of it, the heart of the GNU Radio stuff is, first we start with our USRP source.
Primitive AI.
Yeah.
So this pulls in data at a
interesting
sample rate
thing
of
is,
4.8 megahertz, or megasamples per second.
It's
Our
really,
center frequency
we might
is
have to drink to the end of
125.2
CAPTCHA.
megahertz. So 125
I mean,
megahertz
if AI is that good,
RF
right? I mean,
converter to the
so
handle,
for example, we
and then
run this
200 kilohertz.
You count on to the
we're
fact
actually
that we're
modulating
living
at
in a
400
community.
kilohertz.
And so
But we don't want to
DEF CON, a
listen
couple of
at
years
400
ago, we
kilohertz
started
because
this
there's something called
Mastodon
DC
server,
spike. Any
defcon.social.
software-defined radio is going to give you this giant DC spike, and you want to move away from that. And then you filter out that DC spike, and then you can listen to the actual data you want. We mentioned a couple different SDRs. The reason I chose the BM10 was because it had a high resolution.
While speaking about methodologies, we cannot skip fuzzing because
the Salier logic analyzer. I realized this is also actually pretty nice. It's 50 megasamples per second is also 12 bits. Then we go into a translating FIR filter. This is three things. First is a bandpass filter.
So this particular
first it actually changes the frequency you're at. So we want to go from 125.2 to 125.4. That's where our sound is. So now we're centered on the sound. And the sound is moving up and down. So our signal is some sort of sound wave, but our amplitude modulated signal is at 400 kilohertz. So it's going up and down. So the FIR filter will also then do a bandpass. So now we're saying, I only want what's around the 400 megahertz. Excuse me, 400 kilohertz. Everything else we can
Sammy
ignore.
Camcar.
So we bandpass that out, and then we decimate. Decimate just we bring the sample
Rehashing
rate
a
down
few
to a
things,
more usable sample rate.
but talking about
Then we go
using
into
laser bounce
amplitude
as a
demodulate.
microphone.
So we convert the
Oh,
AM
yeah.
to the,
That's always
to the
fun.
actual sound.
And
Yeah,
So
always
now
strap
we
the
hear
dildo to your
sound, and then we
windows.
save the file. Then we use something called isotope RX.
other
This is absolutely incredible
audible
software. It's commercial
extraction
software,
things like,
but
you
it's
know,
very
determine
good.
what keys being
It's
pressed by
great
the
at
sound of the
spectral
keyboard
repair,
clicking.
and it gives you a spectrograph, so you can actually see
Yeah,
what's happening inside your
gets
signal.
into a bunch of
And then you
stuff.
can do all sorts of things like
And
DS,
then,
D-hum, D-explosive.
Yeah, that kind of stuff makes me want to like start a business.
But it has a lot
And
of
then-
ways that you can then
because you know, like, at,
improve
like,
the signal.
networking
So you can
events,
say,
how,
hey,
like,
I'm going to learn this area of
all the
sound
like, you
where
know, like
there's just a lot
VC kind of
noise.
people that like
Learn
feel
that
like
and
really
apply
smart
it
and
to the rest
important,
of the
or like, you
signal
know,
and
like
remove
just
that
chatting
noise.
up and stuff.
FFmpeg,
It would be
just
so
we
easy
can
to
actually
sell them
convert some
on
things
like a
around.
little like
And then
transmitter
key
that
tap
you
is
can
really
just
the
like
heart of the
stick to your
system for
window
the
for this kind of
keystroke
stuff and just like
extraction. You wanna
freak them
know what
out
the
about like
person's
corporate
typing.
espionage and
And
shit.
I like this guy's
And then
video
get
that
them to
says,
buy
I'm
like a
big
system for like
BMRC,
$5 grand and just like
so
go and just like
Key Tap
stick a
3 is
little
part of this
like motor to the
software
window
where he
basically.
takes
Yeah.
audio
That'd be pretty
and
good.
he's able to then separate out the keystrokes. Now, what's interesting is that when you have a keyboard and you press some keys on it, every key produces a unique sound. Now, we're not recording sound, we're recording vibration.
Joe's
because we're
talking
hitting the
about
laptop and reflecting off.
predicting
And when someone's
passwords from the
typing on that
past
laptop,
to
the
hack the
sound is
future.
just vibration. And vibration matter. So the laptop is vibrating.
Yeah, I like that
It's
heat
literally
map
vibrating.
passwords.
And because every unique key
You've seen
has a
that one and
position,
there's like,
just like if
you
you
know,
hit a
that
drum
nice
with
solid
a
diagonal.
you hit it
Yeah.
in one location, you're producing one sound. If you hit it slightly somewhere else, it produces a slightly different sound. You can record that.
What's really
and you
curious
can
is all black
differentiate those two
pixels.
sounds. Then you can
They
figure
seem
out
really
what they
random where it's
actually
just like
mean.
apparently nobody
Now, on a
uses this
keyboard,
password.
you
It's
don't
like,
know
huh,
what they're typing. You don't actually know what
probably
they're
more
hitting.
interesting than what the
But
passwords
if
are.
you collected over 100 or 200 keystrokes, and you know the language they're typing in, then you can perform analysis and say, and frequency analysis, like what are they actually typing? This is a Zodiac killer. So he would release these puzzles that are essentially substitution ciphers. You can take all encryption and break it down into substitution cipher and transposition cipher.
Fun stuff. There's like a movie night
Just some
5
example, I
that
love the outdoors.
Jess is throwing
So
for
going
her.
in, as well as pointing lasers. So a
Toastmasters
couple
Club.
demonstrations of the setup.
I'm gonna probably get ready and head
Here
over
we can
there.
see
and
what this actually
help her
looks
pack.
like
She's moving tomorrow
as
into
we're
a
pointing
new
the
spot.
laser onto a reflective
So,
surface of a laptop. We'll just
yeah,
see
it's
the
gonna be a
key tap
big day.
software, FFmpeg and
Cool.
key tap running. This is at 10x speed.
Catch you later.
All right. Yeah, and there's game night at Dojo tomorrow night.
Slide, I will do a little
And then
screenshot
flea market
so we can
Sunday.
compare.
Oh yeah, because it's
Again,
the
that's
first one
10x
in August,
speed.
eh?
So here's typing on a keyboard, what I typed, and then
might try
tab 3 was able to recover. This is after going through the setup, after going through GNU Radio, then Isotope RX with a lot of cleanup. Again, I needed to collect at least 3 kilohertz of sound, and also just an example of what the sound actually sounds like. This was playing music inside of a room and then reflecting off the window. And you can hear a little bit of that sound. And that is the project. The challenges, I mean, this was really interesting. How you
Okay,
get
we only have
this whole
one
thing was
time
really
for
a-
one question. I'm sorry.
Signal processing. And the improvements to the laser microphone, the biggest thing to the laser microphone was really getting outside of the sound domain, getting into the radio domain. Once you get into there, then you have a lot more processing capabilities, and you have all the sound, a ton of noise that was there.
Closer to the
is
microphone.
gone. And there are plenty of improvements we can make, we can discuss later, but thank you so much. I appreciate your time.
Guys. Okay, so the question is around cyber liability. Do you think it's going to be hard to do because of all the laws
So we
around
basically
liability?
knew from the person we were dealing with, Michael, when his last access to the wallet was, which was like 2013, I think. So we kind of looked and see like, okay, did anything change? And that's when we saw this increased randomness of generated password. We go, wait, are all of the prior versions doing something that is not random or less random or weaker? And it just happened that the version fell into that. So this applies to everything up to this version, and then we'll talk about sort of what has happened since this version, which we don't actually know is the TLDR of that. Okay, so let's get into the process of what we did. Bruno lives in Germany, I live in Portland, Oregon, and we did a lot of remote work, which was super fun. And for those who know me, like, I don't normally work with a lot of people at one time. I like to sort of hole up and just hack on stuff alone. So it's like finding people to work with is really cool. And it was a lot of fun, like these late night Zoom sessions, sharing screens, like hacking on stuff. We did end up doing some stuff together in person at a conference. It was like, I don't know, 24 or 30 hours straight or something. And then I got on the airplane and fell asleep the entire time. So it was really like a fun example of like true hacking together. It was really cool. So the process, we basically started with some memory analysis, and we'll explain each of these steps. Memory analysis first, static analysis, dynamic analysis, and then we built some custom wrapper to handle all of that. So if you're from the software world, you're probably like, oh, this is like a totally normal thing to do. But from a hardware world, it's like, it was interesting to be able to do it in like a full process, kind of go through everything instead of just dabbling with like, you know, one tool or the other. So that's, you know, kind of go through this process, and then hopefully we profit. Okay, so let's go into the demo of things. We were going to do live demos, but DEF CON really was like, you should just record your demos. So we know the demo gods, blah, 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 but I like to live on the edge. But I finally gave in and said, okay, we're just recording these. So these are videos, and you can play along at home, you know, afterwards and see that we're not lying or anything. So Bruno's going to talk about Cheat Engine, and we'll go into all the other steps.
Yeah, so first we used Cheat Engine, and it's originally made for games. I personally used it as a kid for cheating my favorite single-player game, so I didn't have to grind hundreds of hours to get my gear. And you can actually also use it for hacking. So, hope the video is playing now.
Is it playing? We can't see that it's playing, so yes, okay. Dean is going to be our video thumbs upper for every video. Is that okay?
Perfect.
Okay, Dean says okay.
So what we did here is very simple. So with Cheat Engine you can scan, edit, even you can freeze some parts of the memory so it can't be modified by the program anymore. And here we just searched for the generated password, and we found it, and which means that other password generators, for example, try to decrypt it in some way that you can't extract it from the memory, or try to hide it or remove it after a certain amount of time, because there's a risk involved if you have plain text passwords in the memory, but RoboForm doesn't, and that's already good. You can actually see that it's found twice. That's one time for the GUI, so what is displayed, and one time is in the memory of the internal logic. We found it.
Yeah, and right when we saw that, we're like, oh wait, it's in the clear, perfect. And then I think we were even, there was a couple different, there was like a DLL and an executable, and we're trying to figure out which piece of the code was plopping that into memory. But knowing that was there, we're like, all right, now it's in memory, let's try to find out what routine is actually putting it in the memory, and then kind of working backwards so we could then figure out where the actual password generator routine was happening within this entire blob of stuff. Because RoboForm, again, does not just generate passwords, there's all this other stuff that we had to kind of dig through to find the right thing. So we used Ghidra, thank you NSA, I'll continue to thank the NSA for that. One of the few things I'll thank them for. Or maybe the only thing, actually. So this is kind of, it's gonna show, let's see, I can't see it again, but this is like, this should be a time lapse. Okay, Dean says, yeah, so there's, you know, we're not gonna show the whole process, but we basically started with this giant binary, and we dug down, little by little, starting to label things of what we thought it was, of, oh, that looks like this, and we would change parameters, and look again, and like, oh, sorry, with Ghidra we were just looking at the static side, so things weren't changing. But we basically narrowed it down to a point, and Bruno found this first of like, that call to system time, right? It was like get time, I think it's time 64, and that was like, wait, this piece of code is calling time, and then it's doing some stuff, and then it's calling SRAM, so seeding the pseudo-random number generator. That was a pretty big giveaway, and there was a couple other places where there was the pseudo-random number generator being seeded, but there was no other call to time, and we basically figured out that this section was the section that we were actually interested in. Of this whole piece of code, like these couple lines, where it's calling the system time, manipulating it, which basically what it was doing, because you can press the, every time you press the generate password button, it hits this code. If you press the button more than one time a second, if there was no manipulation of that time, the time wouldn't increase, because this call system time is just returning time in Unix time since 1970, January 1st, 1970, in seconds. So if you hit the button multiple times, they basically added some additional manipulation in there, so you can press the button multiple times within a second and not get the same password. And they basically are just adding a fixed constant, or are they subtracting? Adding or they're subtracting a subtraction.
Yeah, I think this
Something
one.
like that. Yeah, they were it was something that messed us up, and we'll actually talk about that. But they were doing a manipulation, and it basically is just jumping either ahead or backwards in time. So you can still generate the password if you know all of the time. It was just so they couldn't, you know, duplicate the same time in that same button press. So a pretty weak type of manipulation. Then it calls SRAM, and then it goes into the actual password generation routine. I guess what we could have done, and what we were originally thinking is like, oh, we could just pull out that password generating block, put it into our own code, and then just sort of build the wrapper around it. But it was so complicated when we started digging into the function that gets called after that, was just ridiculous, and we didn't really want to go through that process. So we eventually thought, like, okay, if we can confirm this, we'll just build a wrapper that will go and touch those values, and then just let the rest of the code that's in the DLL do its thing. So once we could identify the static portion of code where we knew that pseudo-random number generator was being seeded with time, then we went to x64 debug, and we were actually using x32 debug. And this is our dynamic analysis, to be able to debug the system as it's running in real time and see what was happening with the registers and with other low-level CPU stuff, so then we could see if we could manipulate it. And this is going to be interesting because, again, I can't see stuff here. So we're going to start it. And I'm pretty sure what I'm showing first is there's a bunch of breakpoints that we set, so we can actually, you know, run the code, and then it's going to hit the breakpoint at certain times when certain pieces of code are run. We basically set the breakpoint that we care about at that same spot that I just showed. So when system time is being called, and then I'm probably running the debugger. Eventually, the password generator is going to start. The GUI is going to start, and even when you first start the GUI, there's already one password that's in there. So it actually already runs the password generator once, So that manipulation has already happened once, which for us threw us off again a little bit. And I think it's eventually going to stop, but I'm generating passwords, and if you look, which you probably... Plus, like, whatever manipulation maybe there was from the call before. And has it stopped yet? Is it just sitting still? Still going. Okay, so I'm going to generate a couple passwords, and then at one point I'm going to write down, there was one value that I don't have on this slide, it's on the next slide. I think it's like 66CF6550 in hex for EAX corresponds to one particular password. And that's the one that we're going to end up redoing once we let the system generate some more. Has it stopped? Okay. So this is what we care about out of all of that. The two arrows. There's one arrow pointing to EAX, and then there's one arrow pointing to the password that's been generated. So those two things are completely intertwined. Anytime we enter the EAX value of that particular time, manipulated time value, it's going to generate that particular password. So let's continue on with that part of the demo, and now I'm going to generate another password just to show again that EAX continues to increment because time is incrementing. And then once we get it sort of cleared the EAX value with the new one, then we'll go back and replace it with one we know to show that we can, regenerate passwords that have already been generated from the past. I'm just going to watch your reactions so I'll know when it actually happens. When it does, go ooh or something. Ooh, right? So, so now we have regenerated a password. In theory, with a properly, computationally, cryptographically secure system, that shouldn't happen. But this proved to us with the debugger of like, nice, now we can basically feed in whatever EAX value we want for time. And the manipulation doesn't really matter because that just changes kind of the date range a little bit. But we could precompute everything if we were able to tap right into that part, hook into that part of the DLL, add our wrapper code around it to get to that part. This was pretty cool. Oh, and this is the hacking time, right? So now, do you get it, right? We're hacking time to change that. So that was, yeah. Okay, so then the wrapper code. This was something just to put it all together, give us a way that we could precompute all the passwords that we wanted to for the date range that mattered for us. And we did it in, I think just, what was it? Visual, I don't even remember. It was in Visual Studio, yeah, Visual Studio, and we did it in C, which I know is like taboo now, can't use C, but I use C, and I use assembly language, and it actually was, cool because we had to tap into we had to do some assembly language to move some things around to get it properly executing in the DLL, and C and assembly language really for sort of hardware hackers, that's what you want to see, because that's the type of level that we work with. Scrolling through the code. This is all open source, by the way. It's on my website. There's a link in the slides, and these slides will be up on the DEF CON server after the session, whenever DEF CON puts them up. They're also on my website, which is grandideastudio.com. I put them on that's like my formal website. But everything is there, so you could already work with it, and somebody already has, which we'll talk about. So yeah, this code basically is, let's see. The video is kind of showing different sections, but this first section, we're just setting the time values that we want, the time range that matters. And then it should be scrolling down a little bit, but kind of showing some functions as we're getting ready. We need to have code that's going to hook into the DLL, so it has to search through the DLL. This is not an exported function. Is that the right terminology? It's not a function that you're normally supposed to access from the outside world, right? I see nodding. Okay, so it's something where we know the code is there, but it's not given to the to the other executable to normally be able to work with. So we had to search for a known signature string that we found just by looking in the debugger to say, okay, let's just look for these kind of opcodes and hope that's the right section in the DLL. So we're kind of searching through for that.
Oh,
Yeah.
found out the
Let's see
company
what
that
else we're
screwed me
gonna
over.
Look for so these are all the functions.
They renamed themselves to Evolve.
So yeah.
And
This
then
code here, we're calling system time.
they made
And
this
we're basically setting
fractional
our
COO,
computer
the
at whatever system
co-founder,
time we want.
and they're launching their first product soon. So I looked at my old timelines
And then, there's also
and like Gantt charts
there's
and
some other
stuff,
constants I'll
and
get
they're
into.
on
There's
the
like a bunch of
accelerated
weird stuff that we
timeline.
had to end up doing
which means
it
that
seems
everything that
easy
they
in theory
did
of like,
worked,
oh, let's just hook into
and
this DLL
it
and like,
means that the
call
idea
code.
that they took
But
from me also
things have
worked.
to be prepared
And
before
they were
that
able to
actually
shorten
be
the iteration time on that, so that's some interesting
we are
data,
here? Is it
but
still scrolling,
kind of
or
want to
can
throw
you-
up right now, so.
Still scrolling.
Where
and
are
outstocked.
those guys at?
Alameda,
Okay.
Oh.
So yeah, this is the part that should be
When were
searching through the
you
DLL,
working with them?
finding that
February and March.
portion, finding the address of the DLL
Gotcha.
with those opcodes
Yep.
that we want. That's the exact
Crazy.
same stuff that we
They took
saw
my idea and
in
now they're
x64
fucking
debug
running
and
with
in
it.
Ghidra. The upper memory is going to change though, right? Because we don't know where the DLL is going to be loaded in memory, so we kind of know. But being able to search through it automatically makes sense. And there's a whole bunch of different parameters. I don't know if you noticed on that RoboForm screen, but there's one for
Chief hacker
if you want to use
So I handle a lot of the logistical operations for DEF CON, as well as sort of wrangle a lot of the department leads, like
So we had to figure out
you see
how those
here.
parameters were configured before we could actually call the function that was generating the password. And that took a lot of trial and error and a lot of debugging, and as it should be, right? If it was too easy, it wouldn't be that much fun. But it was really interesting to kind of see that a lot of those values had to be placed in certain
Next
memory
move to
locations and
Android
specific things, and
permissions.
that's what that
After
array at
that,
the
look
beginning
at app
was.
usage data,
Like, we just
then
happened
move
to
on
see
to
that
location
this
data,
setting
drill
is this
down
one,
into
and we have a couple bytes that we don't care about, and then we add another one. And then we get to the cool stuff, which we're basically looping, and we're calling system time, setting all the values the right way, and then we get into the assembly language, which is my favorite part, and I don't really know. I think it's maybe this part that shows the rest of it. But we're moving the parameters into the right spot, we're moving everything into the right spot, and normally what was happening is we were getting crashes for days, right? Or over and over again, and then finally it's like we're going to try another thing, and then it finally worked, and we generated a password. We're like, holy crap. Then we built the loop around it, so we're just doing this over and over again, setting the time, calling the DLL, getting the password out. Because the password gets set into some register that, that's where it was that we saw in Cheat Engine, then we push that into a variable in C, and then we print that out. And turns out it wasn't the most efficient way to do it, but it definitely was enough to generate the passwords. So we had all of our passwords. Is this actually showing the password generator? Oh, it is. Okay, right. So we actually got it working. This is generating all of the passwords starting from whatever 2013 date range we wanted at about 100 passwords per second, which for us was fine because we only had, it was like a couple months worth, so it wasn't a huge amount, and it took, on my machine, I think it took like 20 hours or something, but yours was like super long.
Yeah, I think you had the M2 SSD, so Windows really limits the amount of time.
Yeah, and there was like disk access, right? Yeah.
So I needed like 3 or 4 days.
Yeah, to do the list, right? And that got really frustrating when it's like we tried different password lists that we were generating, plopped them into the password cracker, tried to unlock this Bitcoin wallet, and we kept failing. And we're like, oh my God, is this our coding problem? Are the parameters wrong? Are the dates wrong? We kept calling this guy Michael, and
and he was getting like pretty annoyed.
Yeah.
I was talking to him, and he was like, in the end, he was like, oh no, not again, this guy.
yeah, he's like, oh, they're bugging us again, and and then at one point he was like, I'm gonna see if I can remember it through hypnosis, and we're like, oh boy, now we're in trouble. But it turned out, so he had sent us a list of passwords that he had used for other things, and all of them except one were 20 characters with specials or without, I think. I think some...
he told us he used specials in
Yes.
his original password,
Right.
but there was some which didn't use
Which
special.
didn't, right. So he was so sure it had special characters, but it turns out there was a couple that didn't. So we're like, let's just regenerate without special characters because that changes the entire password that comes out. So we finally did that, and Bruno sends me a message like maybe like 20 minutes after we started running that list.
Yeah.
It's very exciting. And
Yeah, I also didn't thought it would happen because he was so sure. He said like, nah, it was special characters, like 99%. And then we got it.
And then we got it. Yeah, so here we had to block out all this. Thank you. We had to block out all of the transaction history because I know that some of you, if not all of you, would go and try to track it down and now see what this guy's doing and spy on the blockchain and whatever else hackers do these days. But we can see the password was actually generated May 15th, 2013, and that was actually a little earlier than we thought, also, based on the transaction history of
But
stuff.
it could also be that he pressed the button twice, right?
Yeah, right. He could have pressed the button enough to like change where that manipulation was happening.
Because how they did it, they I think increased then the time by a fixed amount, which was like around 8 or 9 days.
Yes, and so it was subtracting a negative number, and that's what threw us off. We thought it was adding, or we thought it was just subtracting the number, but it was subtracting a negative number, which is adding. So we were going the wrong way in time to try to create our list. But ultimately it ended up working, but it was pretty dark for a while. There was a couple days when it was like, we just went through all this reverse engineering work, we can generate all these passwords, and it was like, is all of this work gonna go wasted? I mean, I guess it wouldn't be wasted anyway because other people could use it, but like, from our perspective, it would have been a bummer. As part of this process, sometimes I make YouTube videos, and this was a project where we were like, this would be super fun to film this process and make a fun video out of it to kind of show, you know, the story and the drama. So how many of you have seen our video on this? Oh wow, that's impressive. That's like a quarter maybe. That's good. Everyone else, hopefully you watch it. And these are just some behind the scenes of what it takes to film videos, like without just using your, you know, iPhone. With this particular project, the customer who had this wallet is from Germany, but he was in Barcelona on vacation, and Bruno's in Germany, so we started kind of our process in the video in Germany. We did interviews, and then flew,
so
here's our
you
film
can
crew,
use
by the
them,
way. And then we flew over to Barcelona, and Michael, this guy, thought that we were just going to ask him more questions and interview him again. Like, he didn't know that by that point we had done it. So he was like, oh god, now they're just going to ask more things. So it was actually pretty funny. We're not going to reveal like the full thing, because that's why you should watch the video. It's way more exciting when you watch it there instead of on a tiny screen here. But we basically set up this whole environment like, you know, Publishers Clearinghouse style kind of reveal. Which was totally ridiculous and yeah, very, very fun. And that's part of it, is like being able to share this information and you know, share some technological stuff is super fun, and being able to make videos and like get creative with things that we're doing otherwise equally as fun. So this stuff is really cool. And also you can see how, you know, safety third, for those who actually can see the picture, there's two guys holding a gigantic ladder as one guy's like fiddling with some lamps and electrical stuff. I probably shouldn't have documented that, but definitely not safe. So yeah, once we found this issue and we solved our problem, we're like, awesome, okay, Michael's taken care of, we recovered his Bitcoin, yay. But part of the process of hacking, in my opinion, is sharing that information with other people so they can learn from it and use it, and that's equally as important as the success of the project, right? If you just hoard all your information and not share it with anybody else, what's the point of hacking? I think that's something I feel very strongly about, and something that has been sort of ingrained in me since my younger days of being a hacker. So we solved this problem, and we're like, all right, how are we going to disclose this? You know, there's responsible disclosure, which I don't really like that term because it implies that not doing that is irresponsible. And there's all sorts of things, like when I was at the loft back in a long time ago, we would kind of tell the vendor, like, hey, we're going to release this in a week or whatever, and really force them to fix things. And now there's a little more kind of ethical dilemma about, like, how much time do you give a vendor? Do you tell the vendor? We looked up and went to the RoboForm website, looked around online, looked at different bug bounty platforms, and couldn't find any indication that this company had worked with hackers before, or worked with good faith researchers. So we got really worried, because in this day and age, you sort of expect software companies will have a security at whatever contact or something, right? Like, it was scary to not see that. So we couldn't find it. We started discussing, like, what's the reality of the situation? Are we going to get sued? We know from DEF CON history, there was even a talk, actually, I think, was it supposed to be today, that received a cease and desist letter, and now they're working with lawyers, and maybe they're going to be able to give the talk on Sunday. Like, it's a real risk for researchers, and nobody wants to get sued, especially when it's a company that has lots of lawyers, and we're like individual people that don't want to deal with that. But if it came down to it, we would. And I remember also talking to my wife about this, of like, should we release this information? Like, I really want to talk about it at DEF CON and do something with Bruno, like on stage. And she's like, of course, like, you're a hacker. Like, you need to go against these companies that do it. And if you get sued, at least you'll have given the talk first. Which I agree with. So that's my little rant. So we reached out to Kim Zetter, who is a fantastic journalist with cybersecurity, and has really been pushing, the good of what hackers can do, and also has written some books about some like wild state-sponsored adversary type of stuff. And she wanted to write about the story. So we're like, great, she can reach out to the company and kind of get a sense of how litigious they are, like what's going on. So she wrote the story, reached out to them to get some comment about our work, and they basically were like, oh, we fixed the problem, not a big deal. And then she wrote back and was like, well, how did you fix the problem? Nothing. Crickets. And I thought that was also another kind of indicative thing, right? Of like, okay, if they're not responding, like, it should be very clear, if you fix a security problem, first of all, you should notify all your customers if you make a significant change like that, which didn't happen. But you also want to be very proud of your changes and say, this is what we did to fix it, so you can trust our software that you're running. None of that. It almost feels like I'm in the 90s again, talking about this stuff. So she didn't get any meaningful comment. Article came out, no comment. A lot of journalists reached out, nothing. Maybe this is more typical than I think, but I was really surprised of not getting any sort of feedback. And then we decided, okay, article came out, same time, let's release the video, and then let's do our DEF CON talk. And I think it's a concern. I guess I also want to ask, how many of you have been in the same situation of like finding some vulnerability and being worried about talking to the vendor and getting sued? That's a lot of people. That's probably 25, 30 people just in this room. Multiply that by the number of people at DEF CON, multiply that by the number of people outside who are also hacking. Like, is this a significant enough problem? And vendors know that, but it is a real thing. So anyway, yeah, we released all the information, and I think that's the important way to go. And hopefully, hopefully I don't make my next video from jail or something like that. So some future work, right? So we don't know how they fixed the problem. Maybe future versions, they say they increased the randomness of generated passwords. Maybe they did. We searched through the code. We couldn't find any direct calls to system time. It could have been obfuscated. We don't know. Maybe that's future work. Maybe not for us. Maybe for one of you who go, ooh, let's go dig into this, right, and see what they fixed. Already, since we released our code, our friend Dean Pierce from Portland, 503, has already taken our code and optimized it to be over 600 times faster. Almost probably 1,000 times faster, depending on the machine. Where we were generating 100 passwords a second, Dean was generating 68,000 passwords a second per core. So he made it multi-core, and he removed the need to directly set system time, which requires administrator access, by getting rid of that whole call to system time and just putting a value into that register. So you don't have to call system time, you just plop whatever Unix time you want into there. And then what else did you do? You did one other thing. You don't need to call the DLL each time, which in our code we're calling the DLL because it's like resetting some things that we're not exactly sure about, which takes a lot of time. You're just reseeding the random number generator directly. Okay, so it's knopping out so you're patching a different part of the DLL, knopping out some parts that's reseeding something, so you don't have to keep calling the DLL, which is a huge time savings. And then he made it command line. Our code, you had to like change the parameters, recompile it, run it. His is now command line. You put in your start time, your end time, your parameters, and you let it run. And now you can create your rainbow tables of all of your passwords with the RoboForm password generator that have been computed prior to apparently their fix in 2015 for 7.9.14. And maybe other stuff. Who knows what's going to come out of this? And a couple of resources. Again, these slides will be available. These are clickable links, but all the code is available. All of Dean's code is also available on GitHub and also linked to from the website. And then the original Wired article, and then the video that is on YouTube. So that's our story. about hacking RoboForm. Any last words?
I mean, this should also really put in a perspective that I showed you the examples of the poor seeded random number generators, and it was like standard Unix password manager and Kaspersky. So it is probably
All right, I'm getting one.
things we haven't checked yet, just because we thought, okay, this must be secure. So
Yes, widespread, right? This is not the only thing. It's still happening. Go out there and find random number generators, and you too can also hack time. So thank you for coming.
You know what the protected type is.